Hello, welcome back. You made it through simple interest, and as promised, now we are going to look at compound interest. Compound interest is a little more exciting than simple interest because you have the potential to earn a heck of a lot more, especially over time. And I will show you how. It almost sounds like an infomercial if I'm not careful. Before I show you how, just a couple other terms that you might see as you're doing your reading here. Investment is the use of money to make money, and that's how I keep trying to frame my examples. It's a very positive thought to put money in and try to use your money to make some extra money, interest and things. A fixed investment has guaranteed principal and interest, like a savings account with a certain interest rate. A variable investment, neither the principal nor the interest is guaranteed. Stocks, mutual funds, commercial bonds. Like you can buy stock and you can end up losing everything, or you can end up gaining a ton. It just depends on what's happening with the markets and when you sell and so forth. So that's variable. All right, so as promised, compound interest. Well, let's start with the future value formula that you learned in simple interest. Future value equals the principal times 1 plus RT. Remember, this is derived from thinking about future value as your original principal plus the simple interest that you add to it, the PRT. And then you just factor out P to get that fancy formula. So in our example, we had, in the beginning of the video for that, we had invested $2,000 at an interest rate of 3%. But remember, we go ahead and use the percentages as their decimal format. And we did it for 4 years. So for year one, you have the $2,000 times the 0.03 times 1 to see how much interest you earn. And we found out that it's $60. So the future value at that point is $2,060. And to continue in simple interest, we added $60 each year. It was an arithmetic growth, very linear, because you're adding the same amount year after year. So when we plotted it, we had a nice line. But we don't want to do that with compound interest. We don't want to just figure out the interest for one time period and keep adding that same number. No, this is more exciting because we want to earn interest on interest. So with compound interest, what we would do in year 2 is rather than just add $60 again, we would see how much we have in the bank at that point, and we would compute our interest all over again. With compound interest, year 2, we would say that our principal is now the $2,000 plus the $60. Our rate is still the same. That hasn't changed. That's still the 3% or 0.03. And we'll still think about time as being 1 year because we're just going to look from year to year right now. So we could do the 2,060 times 0.03 to see how much interest we're going to earn that year. I'm putting in my calculator right now, and I'm getting $61.80. So the future value at the end of year 2 would be the 2,060 plus the $61.80, which is $2,121.80. See the difference there? If we were just adding on another $60, we'd have $2,120. But we're already $1.80 ahead. I know you're thinking, woo, I can't even buy a bottle of soda for that. But, whatever. This is just the beginning. You're going to find with exponential growth, it's very gradual at first, and then suddenly it shoots up. In fact, at first, the linear growth might look like it's ahead. But then suddenly exponential growth overtakes it and far exceeds it. So year 3, we would do the 21,2180 times the 0.03 to see how much interest you have at that point in time. And I'm getting $63.65. So the future value for that one, you have the 21.8 plus 63.65. You get, oops, accidentally tapped that, sorry. $2,185.45. Year 4. 21.85.45 times 0.03. You get $65.56. So see how the interest is starting to climb now? So the future value for that one, $2,251.01. So you are now $251.01 ahead with interest. If you had only done simple interest, you would have only added $240. But instead of compound interest, you end up adding $251.01. So you're $11.01 ahead of what you would have been if you'd just been doing simple interest. So that's nice. You know, you might be able to get like half a tank of gas in a small car, but it's better than not earning it, right? But this is something to think about. The more your initial principal and the more time that passes, the more the potential. Because what's happening? Well, when you're compounding annually, like we are right now, you've turned that time into an exponent. Remember earlier we had F equals P times 1 plus RT. Well, now, as we find our future value, we're taking our principal. If we take our principal times, we take our principal times 0.03 to get interest. But if you take your principal times 1.03, that'll immediately jump you into your future value. And each new year, we would times by the 1.03 again. So for what we were just doing, we started out with $2,000. And if you times by 1.03 one time, that'll give you your future value at year 1. Times by 1.03 a second time, that's your future value at the end of year 2. By 1.03 a third time, that's your future value at the end of year 3. Times 1.03 a fourth time, that's your future value at the end of year 4. The T is 4. So each year you're multiplying by the rates to get you principal interest earned on interest. So right now, if I do 1.03 to the 4th power on my calculator, remember, order of operations, you got to do that exponent before you can multiply by 2,000. I get 1.12550,881. And then I times that by 2,000, and I get 2251.01762. Well, look, it's a little bit off. Because know how we rounded earlier when we were going along? We rounded at some point with some of those pennies. So it's a slightly different, but that's just a rounding issue. If you want to make sure you don't end up with that problem, just don't round when you're working it until the very end. But there you go. So that tells you your future value if you do compound interest yearly after, so many years. Pretty cool, huh? So initial principal, this will get that B is your future value. The balance, the full balance that'll be in there at the end of your time period. Pretty neat, huh? So let's see, I was debating whether to do another example with you on that, but you know what? I'm not going to. I'm going to move in now and talk about the fact that we're not just going to do annual. We're not just going to look at compounding annually. We're going to have other situations too. Semi-annually. So 2 times a year. We're going to look at quarterly. All kinds of them. 4 times a year. Going to look at monthly. 12 times a year. So compounding periods means how often are we going to stop, look at what's in our account, and compute interest based on that exact moment in time, what's in our account. We pause, compute and add interest, and then move on. So like it's semi-annually, you pause in the middle of the year, see how much is in the account right then and there, compute your interest on that, add it in, boom, continue the rest of the year. At the end of the year, what do you have in your account then and there? Figure out the interest, add it in, boom. You do that year after year. Quarterly, you do that 4 times a year. You know, after 3 months, you stop and look at what's in your account, compute the interest based on that time period, add it in, move on. And the thing with this though is when you start compounding, you have to introduce the number of compounding periods. And we usually use the letter n, little n to do that, lowercase n. So your exponent's going to change. Like right now, our exponent here, t, is based on years. Because the 1 plus r, that'll tell you how many times you gotta multiply the 1 plus r, like the 1.03. But if you're going to do it twice a year, you're now going to have to do double that, so 2t. If you're going to do it 3 times a year or 4 times a year quarterly, you're going to do it 4t times. So you're going to have to end up multiplying that t by your number of compounding periods in the year. If it's daily, you might have to think if probably 360 days, because that's usually what you use, unless you're told otherwise. If you're told otherwise, then you'll know to use 365. So there's that. And then the interest rate, like everything so far that we're doing right here is an annual interest rate, annual time. But if you're going to start looking at it parts of the year, you're going to have to divide that interest rate too by those numbers. Like if you're looking at it quarterly, your yearly interest rate has to be divided by 4 to get a quarterly interest rate. So you're going to introduce the division by n underneath that r as well. And you'll see that your book changes the formula. So like what I was just saying, okay, b equals p times 1 plus r to the t, right? Well, if we're going to start doing things with compounding periods, we're going to have to use that in. Because we're going to have to be able to look at, well, if it's, like let's say it's compounded quarterly, that's 4 times a year. And then 4 times the number of years is how many times to compute the interest. And then the r over 4 will change the yearly rate to a quarterly rate. So whatever your n is, like whatever your compounding periods are, that's what's going to need to go in there. And you'll find that your book, instead of saying B for balance, they're going to use a capital A for future value. And it looks like this. Your compound interest formula, interest computed on the principal and accumulated interest. This will give you your future value. So it's a little different than the simple interest formula that I equals PRT spits out your interest. You still got to add it back in to get your future value. This formula spits out your future value. And then you got to do a little subtracting if you want to see what the interest is. So interest computed on the principal and accumulated interest. A equals P times 1 plus R over N to the NT. A is your total amount after your given period of time. R is your interest rate as a decimal. P is the initial principal being invested. T is the time in years. N is the number of compounding periods in 1 year. Okay, here's an example. How to do this. Mary wins $2,500 in a singing contest. That's a pretty impressive purse for a singing contest. She invests in a 4-year CD. That has 3% interest, compounded monthly. We want to see, well, how much will be in there so that when she cashes it in. How much will she get when she cashes it in at 4 years? Okay, so we're trying to find A. Trying to figure out how much is going to come back to her. So she's going to get her $2,500 back plus whatever interest she got. The initial P that she's investing is the $2,500. The R is the 3%, but we're going to use 0.03. And T is 4 years. It's compounded monthly, so N is 12. So let's put that into our formula. A equals P times 1 plus R over N raised to the NT. So we got $2,500 times 1 plus 0.03 over 4 raised to the 4 times... Oh, I'm sorry, not 4. I made a mistake there. Sorry. I'm being distracted right now. Somebody's banging something in the other room. That's what happens when you're trying to do this at home. All right, over 12. I have laundry in the dryer, and I'm trying to figure out what the heck the crashing banging is. Anyways, 12 times 4. Okay, so principal is $2,500. 1 plus 0.03 over 12 raised to the 12 times 4. All right, we do have to follow order of operations, so we have to be really careful here. So in the parentheses, I need to do the parentheses first. Honestly, that little exponent, 12 times 4, we can go ahead and multiply that and say 48. There's nothing wrong with just going ahead and taking care of that little multiplication. But in the parentheses, we got to do the 0.03 divided by 12. So we have 1 plus 0.0025. And then when we add the 1 to that, we just have 1.0025. And that's raised to the 48th power. So I just put that in my calculator. I'm not going to touch anything else in my calculator until I'm done. But when I raise 1.0025 to the 48th power, I get 1.127328021. Isn't that like a lovely decimal there? And then just go ahead and in my calculator say times 2,500. And I get 2818.320053. The original problem doesn't say I have to round a particular way, so I just go ahead and assume I'm going to round to the nearest cent. So Mary, when she cashes out her CD, will have $2,818.32 coming her way. So since the original principal was $2,500, she will earn $28,1832 minus $2,500. So $318.32 in interest, and from that CD. Okay. So I think the biggest things with this formula are, first, memorizing it. You do want to know it. And then second, making sure to follow the order of operations. You're going to need to simplify the r over n and then add the 1. Raise that to your exponent after multiplying the n and t. Then multiply by your principal. In this case, the 2,500. That's the order you got to follow. If you do that, you'll be good. Keep it in your calculator until the very end, then round it at the very end. That's the formula. A little different than if she'd done simple interest. If she just done simple interest yearly, $2,500 at 3%, $2,500 times 0.03, she would have added on $75 a year. So she would have earned $300 in interest. So in this case, she ends up earning $18.32 more in interest than she would have earned in a simple interest savings account. But yeah, the growth here that results from this is an example of geometric or exponential growth, because you're multiplying the balance by the same number for each time period. It says greater than 1 because it's the 1 plus the interest rate. So like if 3% interest rate, it's 1.03. Each year or each time period or whatever, you're going to be multiplying by that same number. If we look back up at our previous example, at the original example, we had what? 2,060, then 2,121.80, then let's see, I'm going to try to draw a little graph just to show you that. Although it'd probably be better to go to Desmos and do it, but I don't know. So if this is time, 1, 2, 3, 4 years, and let's see, that very initial example started out at $2,000 and got to $2251.02 or so, $2251. So we could probably say, let's say this starts at 2,000. Little squiggly says that we've like scrunched this with the numbers. The scale is scrunched right there. And then maybe I show it by $50 a pop. So going back up, year 1, she was at the 2060, and then year 2, 2180, right? 2060. So about right there. And then year 2, 2180. So roughly right there. Keep in mind, I'm just kind of approximating where this goes. Year 3, it was 2185, and then year 4 was 2251. So 2185 and 2251. Oop, went too far, sorry. 2185. So roughly there. And then all of a sudden 2251. So there. So this starts curving. It's not straight. It's going to be a curve. And then as time goes on, you're going to see that curve. It's kind of gradual at first, but then suddenly it's going to shoot up like that over time. So that's the whole exponential growth kind of thing. It's kind of exciting. It's gradual at first, but it is more curvy than it is straight. All right. Sometimes you're interested in knowing, well, how much do I need to invest today so that I can meet a certain goal in the future? And the present value formula lets you do that Basically, it's the formula we just did, but we just divided both sides by the 1 plus r over n to the nt. So now you can solve for P, or principal. How much principal do I need to invest today so I have the future value A at this interest rate with this compounding information? So I think I had, it's an example of a guy starting a new business. A guy named Mr. Fink. He actually used to be an adjunct for us. It's funny because one of our recently retired math professors actually had Mr. Fink as his high school math teacher, and then later Mr. Fink came and was an adjunct for us. But anyways, Mr. Fink's goal is to have $26,000. So that's the A. In order to start a new lawnmower repair business when he retires in 15 years. So the 15 years is the T. That's when he's going to retire. How much should he invest now in a CD that pays 2% interest, 0.02, compounded quarterly? So N is 4 times a year. So what should he invest now? So we got to find P. All right. So A is 26,000. That goes up top. R is 0.02. N is 4. Raised to the 4 times 15. All right, so we got to do order of operations again. 26,000 for now. It's just going to sit up top. Honestly, you can go and do 4 times 15 and say it's 60. That's up there in the exponent, so you can go ahead and do that. But you are going to need to divide 0.02 by 4. And you get 0.005. So you're going to have, on the bottom there, 1.005 raised to the 60th power. So if you go to do that in your calculator, you might want to say, well, calculators follow order of operations, but let me go ahead and do 1.005 raised to the 60th power just to show you what that decimal looks like. You should be able to do 26,000 divided by 1.005 to the 60th power, but you got to make sure the calculator knows that you're just raising 1.005 to the 60th power. So just be really careful with that. You might have to just to double make sure, maybe force things with some parentheses. All right. So then we're going to do 26,000 divided by that decimal. And I get 19,275.6771. So remember, unless it says otherwise, just round to the nearest cent. So $19,275.68. So that's what Mr. Fink needs to invest today to have exactly $26,000 in the future for his lawnmower business when he retires in 15 years at 2% compounded quarterly. So there you go. And two more topics. Annual percentage yield. Sometimes, I remember being a little kid and standing in line at the bank with my mom, and I remember seeing these little signs on the walls with these little plastic numbers that they would change regularly. And it would talk about accounts, and it would show like interest rates, and it would show APY. I always wondered what that was, and I always wondered why it was different. But the APY, annual percentage yield, can also be called the effective annual yield. It's the simple interest rate that yields the same amount of interest as the compound rate over a given period of time. So like if they give you the compound interest rate, you can find the annual percentage rate, the annual percentage yield. You can find the simple interest rate that would give you the same amount at the end of that time period. To do this, just use $1 for your initial principal. Use 1 year for your time. Make that easy. Plug in all your information into your compound interest formula. And when you're done, you'll be able to subtract 1 and get the rate as a decimal. So for example, let's say you're $1 invested for 1 year, but what they quote you is the compound interest rate of 4.75% compounded monthly. If you put that right now into your compound interest formula, that would tell you how much interest you would make, in 1 year on $1 at 4.75% compounded monthly. And that's exactly what we're going to do. We're going to put that into our compound interest formula. I don't know any funny songs to try to remember this formula. Maybe there's something out there. I don't know. If you guys know something cool, maybe share it in the Muddy's Clearest Points discussions or something, because I'm sure others would love a hint on a way to remember this formula. But anyhow, we're just investing $1. The rate is 4.75%, but we're going to put in 0.0475 because we got to put it in its decimal format. Compounded monthly means N is 12, and we're only doing it for 1 year, so T is 1. So I have 1 plus whatever 0.0475 divided by 12 is. I get 0.003958333, and that whole thing is going to be raised to the 12th power. So you have 1.003958333 going to be raised to the 12th power. So you got 1 times 1.048547881. So 1.048547881. So basically, you would have $1.05 in the account. The 5 cents is the interest earned. If you go ahead and subtract 1 from that, the 0.048547881, change that to a percent, we get 4.85%. This is the APY. This is the simple interest rate. That at the very beginning, if you'd used this as your simple interest rate and done, $1 times a year, you would have ended up with the same amount. Because if you do I equals PRT, it was $1 at this rate, 0.0485 times 1 year would have earned you, 5 cents interest. So it's just another way of explaining what's happening with the account. Like if you don't want to try to explain to somebody the entire big compound interest formula, which can be a pain, instead you can say, well, let's do simple interest, but we have to use this other rate for it to come out the same in the end. So that's kind of interesting, isn't it? 4.75%, it's a lower interest rate when you compound it versus when you do simple interest. But that makes sense. Simple interest needs a higher interest rate in order to make up for the extra that you earn in compound interest because of the compounding periods, because of the exponential growth. When something's linear growth, you're going to need a higher rate to make it match up. All right, one more piece of excitement. Continuously compounding. You're not going to find this at the bank, but understanding the formula for continuously compounding can help you with other types of scenarios, like with exponential growth. Similar formulas used like with like decay and growth and stuff in science. But I like to call it the PERT formula. We use the number E. If you look at your scientific calculator very carefully, you'll find E somewhere. I have a TI 30XA, and I have an E to the X up above the ln button. So like I could do second function e to the x. I mean, I could do 1, second function ln. That'll tell me what e equals. But e's a number. 2.7182812. It's a number. You'll see it in science class too. If you remember taking college algebra, or if you ever took college algebra, or if you took algebra in high school, you probably saw natural logs and e's there, like log base e. But yeah, it's a number. But if we wanted to pretend that our compounding periods were infinite, not yearly, not monthly, not daily, not even by the minute or second, but infinite, like just squeeze infinite number into your year or whatever, then we could use this formula to see how much interest you would make. All right. So let's revisit the example. Let's come full circle back to the example from the beginning of this video. P is $2,000, R is 3%, T is 4 years. And let's pretend we're compounding continuously. F equals PERT. So it's principal of $2,000 times E to the 0.03 times 4. So 0.03 times 4 is 0.12. So we're going to do e to the 0.12 first. So I got 2,000 times 1.127496852. You multiply that by the $2,000. You get 2254.993703. So basically, at the end of your time period, you would have $2,254.99 in there. So in 4 years, if your interest is compounded continuously, like nonstop, not these little finite measurements of time like monthly or daily or anything like that, but continuously, that would be where you end up. A little different picture than, like earlier we had done it back here. Not Mr. Fink, a little further back, all the way back. I'm sorry for making you dizzy. But we'd had what, $2,251.01 in there after 4 years when we compounded yearly. Isn't that kind of interesting? 2251.01 versus 2254.99. So compounding yearly versus compounding continuously. Continuously did earn us more interest, but it's not as much as you might have imagined. Like you think about, oh, compounding like infinite periods seems like that should make it blow up right away, but not as much. But again, give it more time. That's why those of you who are young and still in high school or just starting out of high school, people will tell you, try to start investing now, especially for retirement and things, because no matter what the investments, like these are kind of simplified versions of different investments, but no matter what the investment, time is on your side. The more time you can give it, the more time for growth. If you do something with compound interest, you have that chance for that exponential growth to really take off before you need the money. So that's the lesson, the life lesson for today. So there you go. Well, that about covers what we're doing in compound interest. When I talk to you again, we will talk a little bit about installment buying, and we're going to get into eventually buying a house. Fun times, right? All right. Thank you for joining me.